this didn't die, did it? No, we're good. Hey, we're back. We're still in chapter 1. Today we're at the beach. We're at Ocean Beach in San Francisco. We're going to keep going with the lesson. I'm going to try to record maybe like 3. Maybe just like get through this chapter here today. Alright, so let's keep going. So we've got reliability. Everybody has an intuitive idea of what it means for something to be reliable or unreliable. For software, typical expectations include the application performs the function that the user expected. It can tolerate the user making mistakes or using the software in unexpected ways. Its performance is good enough for the required use case under the expected load and data volume. The system prevents any unauthorized access and abuse. If all of those things together mean working correctly, then we can understand reliability as meaning roughly continuing to work correctly even when things go wrong. The things that can go wrong are called faults, and systems that anticipate faults and can cope with them are called fault-tolerant or resilient. The former term is slightly misleading. It suggests that we can make a system tolerant of every possible kind of fault, which in reality is not feasible. If the entire planet Earth and all servers on it were swallowed by a blank hole, tolerance of that fault would require web hosting in space. And good luck getting that budget item approved. So it only makes sense to talk about tolerating certain types of faults. Note that a fault is not the same as a failure. A fault is usually defined as one component of the system deviating from its spec, whereas a failure is when the system as a whole stops providing the required service to the user. It is impossible to reduce the probability of a fault to 0. Therefore, it is usually best to design fault tolerance mechanisms that prevent faults from causing failures. In this book, we cover several techniques for building reliable systems from unreliable parts. Counterintuitively, in such fault-tolerant systems, it can make sense to increase the rate of faults by triggering them deliberately. For example, by randomly killing individual processes without warning. Many critical bugs are actually due to poor error handling. By deliberately inducing faults, you ensure that the fault tolerance machinery is continually exercised and tested, which can increase your confidence that faults will be handled correctly when they occur naturally. The Netflix Chaos Monkey is an example of this approach. Although we generally prefer tolerating faults over preventing faults, there are cases where prevention is better than cure because no cure exists. This is the case with security matters, for example. If an attacker has compromised a system and gained access to sensitive data, that event cannot be undone. However, this book mostly deals with the kind of faults that can be cured, as described in the following sections. Hardware faults. Okay, so sorry. Let's